Hey everybody, I'm sitting outside because the weather's so nice and I figured I might as well do a little work. And I hope you're enjoying your Saturday because it's pretty nice outside. But anyway, let's get to the point. There are some takeaways we should all be focusing on from the this week's practice tests. And again, this is an opportunity to learn. I'm not picking on anybody at all. It's just these were a lot of common mistakes, and that's why we need to address them. So one of the first things I noticed is that we're not drawing arrows to the proper length. Um, they say we're not going to be drawing during the AP exam. However, I don't know, they may ask, like, why should they be the same length? Then you just have to be able to explain that. So, if the acceleration's zero or it's not zero, be able to explain why. The previous week we had a circular motion one. The net force is always towards the center. That's why you drew the arrow towards the center larger than the one that was away from the center. Something like that, they may ask you to be able to explain. A lot of you in the spring problem missed some key phrases like at rest. If you hear at rest, please immediately go to the fact that the acceleration is zero, because that's basically what they're telling you. But look for other keywords like stationary or suspended or hover. But these are key phrases you want to get used to picking up on. And you already know if an object starts from rest and increases speed to a positive v, well, that's a different story. Then a is not zero. But if it just says the object is rest and it doesn't mention anything after that, assume acceleration zero. Another thing, silly people, if you're asked to draw a free body diagram, odds are you should use Newton's second law, sum of the forces equals ma. Because a lot of you are like, oh, free body diagram, let's use energy. No. Don't go there. If it's an FBD, you're probably using Newton's second law. If time's involved, you're probably not using energy, because time is not a variable in any of the energy equations that we have. So keep that one definitely in the back of your mind, because some of you were asking through emails, like, when do I use energy and when do you not? You're probably not going to use energy if time is involved. Time leads to kinematics. Kinematics leads to acceleration, which leads to F equals ma. Now, another thing that we should definitely take away from this week is which equation. Now, many of you got this wrong. It's okay. Let's take a moment to think about it. So when I was in college and we did an algebra-based course, one of the things they told us to do is always test your equation to make sure it makes sense. Do the units make sense? That's a good check. And do the limits make sense? So I was always told to try to sub in infinity or zero. So take the first one, for example. If you sub in zero, which we weren't allowed to do, but I'm just saying, we had it sub in values of 1/2 T1 or larger. But if we subbed in zero, you'd get a negative torque. I don't know how that would be possible, considering anything was moving to the right. And then if you plug in zero for the other one, you get a positive torque. That may not be the best example of this, but the infinity, throw in infinity. If you throw in infinity for the first equation, the torque approaches infinity. Now, we were dripping oil on this thing, so the frictional torque caused by the should be reduced because of the oil. That doesn't make any sense. If you throw in infinity for the second equation, where you're dividing by t plus 1/2 T1, all of a sudden that torque goes to nearly zero. So really, that's a good little nugget to keep in the back of your mind as you move forward into the real test. If they ever ask which equation to use, good strategy. What happens if you sub in zero to each equation? Does what happened make sense? What happens if you sub in infinity? Does what happened make sense? Now, for those that use energy, since there were so many of you, I think it's worth discussing why it didn't work. You correctly said that there was no kinetic energy and there was no gravitational potential energy. But then you did something different. Some of you said that the object starts with spring energy, that's in the red here, and then work was done by friction and you end with no energy. A couple issues with that. The object didn't start with spring energy. This object was at rest when the spring was at maximum strength. Therefore, it had spring energy. It didn't move from that spot, so friction didn't do any work. That doesn't make sense. So what you were saying is that it initially was with spring energy, and then friction did negative work, and then there was no energy at the end. But at the end was the same as the beginning. The spring was stretched. It had spring energy, so that doesn't work. In the blue, some of you said that the negative work done by friction gave the thing spring energy. That also doesn't make sense. Spring energy can't be negative. And again, this thing was at rest. So it was a common errors, but I hope we can take away a bunch of good things that we could take with us when we're taking the exam, some strategies. And then there was practice number 4. So practice number 4, personally, I thought was a little more difficult, and I thought you had a tougher time with it, but that's okay. That's why we're practicing, and we need to talk about some of the things we can take away from this. So one of the things was that it says that the student makes the following claims, and I think it was twice the energy at the bottom, and the object should move twice as far. You need to focus, like when they say what the student is saying is correct, you should focus on those claims and just, one of them was energy at the bottom. Do you agree with that? Yes or no? Say so. Did it go twice as far? Say so. I think one of the other claims was if you have double the horizontal distance at the bottom, that would give it twice the height when it comes to the incline. Again, focus on addressing the claims. A lot of you did some good stuff, but you never addressed the question, which was what part of the student's claims are correct? First, what was the student's claims? Second, what do you agree with? So in the future, if we get another question like that, be sure to just take a note. What are the student claims and focus on addressing them. So another great strategy that a lot of you used is that you did math first, and that's great. I mean, in terms of claim, evidence, reasoning, you make a claim, your evidence is often your math, and then your reasoning is your ability to discuss how the math agrees with your claim. So keep doing that. That was lovely. But some of you had contradicting math and claim. So that's dangerous because one of them could be wrong. But if you do notice that it's drastically different, then maybe you should go back and take a look. I know the time is going to be limited on the test, but think about it. So another thing was whether or not the kinetic energy was linear or curved. So this is a good one. It's actually definitely worth talking about. So at the bottom of the incline, the object starts with kinetic energy. There's work done by friction to bring the energy to zero, to bring it to a stop. And this is asking you to graph kinetic energy versus position. And that's what's important. This is KE versus position. That's huge. Because if you look at this equation, and not using the 1/2 mv squared, I know the v squared makes you want to make it curved, but let's focus on, they wanted you to graph kinetic energy versus position. There is a direct relationship between these two. There's no squares in here. If you have, half the distance or you've gone double the distance, you have half the kinetic energy left, depending on how you look at it. So when it's versus position in this case, it's definitely a direct or linear relationship. Same thing can be said if you drop an object. So in this example, I have you start with potential energy, the thing is dropped from rest, and we want to know about how the kinetic energy changes. So again, if it's based on the height, if you go down halfway, you'll have half the kinetic energy. So that's a direct relationship, which means that it would be a linear graph. Now, when is it curved? That's when it's versus time. That's just basically what is the velocity at some time. And there's your squared relationship right there, v squared. And I don't know, I guess that's really it. I know that's tricky, and it was only 1 point, but I thought a lot of you missed it or did well on it, but it's definitely worth discussing. So yeah, I put it in here. When it's versus position, it's generally linear, and if it's versus time, the kinetic energy should be curved. Now, the thing that brought back horrible memories of an arrow hitting a pumpkin FRQ and was most missed, and thank God this wasn't a real test and we're having an opportunity to learn from this, is number 4. You need to know, if you see collision, this means momentum. So many of you did like, oh, collision, and it's even asking me to graph momentum. Let me talk about energy. No, please don't do that. When two objects collide, they have equal and opposite changes in momentum. That is like the most important concept when it comes to this stuff. That makes the answer super easy. You don't even have to do math for that one question with the puck hitting the rod. Please, this was the same strategy with the pumpkin. When it was a pumpkin, some of you were like, well, it's an elastic collision or it's perfectly, who cares? Do not discuss the type of collision unless they ask you to do so. The most important concept, if I'm not making myself clear, is that when two objects collide, they have equal and opposite changes in momentum. So in scenario one, which is kind of like here, the puck is moving up and then it's moving down. I just assumed v and then negative v. The change in velocity is negative 2v. When you multiply by the mass, that'll be your momentum, but that's a big change. In the second scenario, the puck hits and comes to a stop. So it was going v, then it's 0. That's a change of negative v. In the third scenario, the puck was moving with a speed v, and then it kind of like stuck to it. So it kept moving forward. I just called that 1/2 v for this example. And the change is negative 1/2 v. So the biggest change is scenario one, where the change was negative 2v. That's bigger than negative v. It has nothing to do with negative being smaller. Therefore, in this case, the rod will have the biggest change in velocity. This case here in the middle, where it's negative v, the rod will have the second most biggest change, and the third one, as you know. So please, this is a really simple, easy one to do. When two objects collide, they have equal and opposite changes in momentum, and the biggest change in velocity was the one that bounced back. Again, many of you got this, but a lot of you kind of went into trying to do conservation of energy. Don't do that. You talked about the types of collisions and energy conserved in them. Don't do that. It's a collision. Focus on momentum. Not to say that some of the energy stuff you said was incorrect. It just didn't lead you to the right answer. So keep that in the back of your mind. Some other good things real quick, just some positives. You guys are still crushing it. I'm very confident. You're averaging a 4 as a class, and I don't know. I keep thinking to myself that I'm impressed with how much you're able to recall. I don't know if you're doing stuff on the side to try and remember or look things up. I'm not upset if you are. That's the whole point of this. I mean, you should try and do it on your own, but you're really doing well. So I hope that continues. Keep doing what you're doing. If you have to look at notes, it's not good, but it is an opportunity to study. So whatever it is, I just want you to do really well on this test. And that's about it. So I'm going to get back to reading a book and sitting outside in this beautiful Saturday weather. And I hope you are enjoying yours. Email me if you have any questions. FaceTime me if you want to talk. See you later.